screen. So
Okay.
yeah, you can see here.
Yes, we can see your screen.
Okay.
Fine. So go ahead.
Hello, I'm Alix Nouvelle-de-la-Flèche, and I am a PhD student at IREP and supervised by Jean-Luc Atteya. And I am working in the calibration and the characterization of the performances of the camera CAGIRE. So today we'll speak about the first test we did at IREP for the performances of the camera. So, well, before speaking about the performances of the detector, I will speak a little bit about the context, the scientific one, and the specificities of the detector, and then about the characterization strategy, and then I will speak about the performances of the detector in terms of noise and how we want to measure and to estimate the flux with this camera. So first, just to quickly remind about the scientific context and why do we need the infrared with CAGIRE. So the first thing is that, well, because of the Lyman limit, distant observer sees only wavelength greater than 91.2 nanometers in the source reference frame. But then this wavelength is shifted to the red because of the redshift. So here you have the formula, and here an example of the cutoff because of the Lyman limit here, seen by CAGIRE, so in the infrared here, and in the visible channel here. So one of the first reasons is that the afterglow of gamma ray burst with the high redshift, so for example, superior to 6, is detectable only in the infrared. So that's the first reason why we need infrared with CAGIRE. And well, another one is that some bursts are attenuated by the dust at visible wavelength, but they are detectable into the infrared. So it could help us to detect the afterglow of some burst thanks to the infrared. So that's the motivation. So to speak a little bit about CAGIRE, so CAGIRE is for capturing gamma ray burst infrared emission, and the camera will be located at 1 Foci of colibri. So it will be able to detect wavelengths between 1.1 and 1.8 micrometers. And so the motivation are to monitor and detect GRB afterglows, including our high redshift candidates. So this camera will be equipped with a 2K by 2K detector developed by LINRED. And so CAGIRE, so here the picture is not at scale, but CAGIRE will be located, the detector will be located here, seen from colibri. And well, the fact that we are working with this type of camera in this type of telescope has got some constraints of operability. So first, the detector needs to operate at a stable temperature of 100 Kelvin. And so it needs to be into a cryostat. So this is a constraint because Colibri is a robotic telescope, so the cryostat will be constantly under rotation during the observation. And so that means that we can't let the cryostat under pumping. So we need to have a cryogenic vacuum for at least 6 months to be able to have the good temperature into the cryostat. So that's the main constraint, well, the constraint I wanted to speak about. And so now the camera is composed of different parts. First, we have detector alpha for astronomical large format array. So it's the detector developed by LINRED. It is composed of a detection layer here, so that's what we call the detection chain. So here you have some pictures of the detection layer, which is at CA for the moment. Here it's the ROIC plus the preamplifier, and here they are in the box. And here you have the new generation controller for these two box and the PC. So yeah, that's how CAGIRE is the composition of the camera. And so now I will speak a little bit about the characterization strategy. So currently the detector is at CEA until March 2022. And so for the moment, CEA is conducting detailed characterization of all the detectors, all the alpha detectors, to approve the detection chain, and they are doing that according to ESA specification. So during this time, they provide us some data, and at CPPM and at IRAP, we are working on this data, and we also are working with an engineering chain, so without the detection layer, but with the preamplifier, the readout electronic, the NGC. So that's the first step of the characterization. And then in March 2022, the detector should be sent to CPPM in Marseille, where the characterization will be about the performances of the detection chain for CAGIRE. So we will measure the reference for the detector performances, and well, the measurement will be done with the operating parameters for CAGIRE. And then after that, the detector will be sent to IRAP in October 2022, we hope. And at that point, we want to characterize the camera, CAGIRE, with the optics and all the elements. And so it will be a complete characterization of the camera. And when this will be finished, the camera, all the camera should be delivered to Mexico in April 2023. So that's for the characterization strategy. And now I will speak about the performances of one of the detector provided by the CEA, the one we hope to have for CAGIRE. Well, as I said, for the moment at IRAP, we don't have the detector, so we work with data provided by the CEA, done with the wall detection chain. It could be data into the dark or into illumination with different type of resets. And we also work with a file from CPPM measured without the detection layer. So we'll the whole chain, but not the detection layer, to work on the characteristics of all the other parts of the detection chain. So, well, before going further into the characterization, we have to understand how CAGIRE works. So, CAGIRE will work during a series of short exposures during which pixels are read every 1.3 seconds. So it means that the detectors continuously accumulate the charges during the exposure. This accumulation should be proportional to the flux received by the detector, and this creates a ramp of the output signal. So it's why we call this mode the ramp mode. And so here each point corresponds to a read of the detector, a readout of the detector. So here the ramps are measured into ADU units, but they can be converted to electrons thanks to conversion gain, which is estimated at 7.5 electrons per ADU. So the first thing we can characterize on this detector is the readout noise. So the readout noise mainly comes from the transistors used to read the detector. It can be generated at two levels, at the pixel level. So this is a completely independent source of noise and it's difficult to remove. And it could also be generated at the readout channel level. So because the detector is composed of 32 readout channels, and with each channel has got a common polarization and common clocks. And so that generates a common noise to hold the pixels of a readout channel. And that's what we call the common mode, and it's a correlated noise. So to look at the noise on this type of detector, we look at the fluctuation of the pixels when they are in the dark, because they deliver a signal, and we can look at this fluctuation even in the dark. So to measure the readout noise, we first measure what we call the TDS noise, which is the temporal measurement of the noise. So the idea is that we acquire a ramp into the dark here of the signal. Then we subtract 4 consecutive frames to create a new CDS ramp. And then we compute the temporal noise, the standard deviation of these points over the time. And well, this standard deviation divided by square root of 2 root square of 2 is the temporal noise per pixel. So here you have a map of the noise measured on this detector by pixel, and here the associated histogram. So that's the method, but to measure the noise, it is a method to measure the noise, but the objective is to reduce the noise from the common modes of the RIC. So our detector is composed of here the purple zone of sensitive pixels, and they are surrounded by reference pixels in green. And these pixels have the same electronic than the sensitive ones, but they are not sensitive to light. And thanks to this pixel, and relying on an article written by Bogdan about the impact of common modes, we can correct the sensitive area from the common mode noise thanks to these reference pixels. So that's what we have done on this detector. So we have done that with 2 types of data. The first one with the whole detection chain, here, the science detector, and also with the detection chain without the detection layer, so here called RIC. So we can see that here the correction allows us to reduce significantly the noise. So in terms of readout noise in electrons, we reach 30 electrons of noise, which is quite good. And here you have a map before and after correction by reference pixels, so we can see that the correction is quite efficient. Well, so that's the first result, but we can also notice that we have a significantly lower noise with only the RIC than with the scientific detector. And well, that's something we didn't expect it, because the common modes should be coming from the RIC, mostly from the RIC. So, well, this is something still under, the difference is still under investigation, and we don't really know why we have this difference. So that's all for the noise, and now I will speak about the flux estimation. So here you have a ramp of the signal, and the first thing we do to compute the flux thanks to this ramp is to select the first part of the ramp, because I said before that the output signal was proportional to the flux received by the detector. But in this type of detector, it's not completely true. And we can see here that the output signal is not completely linear. So we want to work on a part of the ramp where there is not too much non-linearities. So we select well, when we go too far too close to the saturation level here, we go into these non-linearities. So the idea is to select the 80% first part of the ramp before saturation. So we compute this level for each pixels, because it is not the same for each pixels of the detector. And then we correct the frames by the reference pixels to remove the noise. Then, thanks to this ramp corrected, we create a series of differential images. You can see here with the useful part here. So it means that we compute the difference between two consecutive frames. And then we will fit this series of differential images. So we work on differential images because it permits to consider the experimental errors as constant when computing the fit, which is not the case with the whole ramp, well, the initial ramp. So we fit this part, but we have several different models to fit this part. So we selected two models, the first and the second order polynomial, to see the one who fits the best this part of the ramp. So to do that, we fit our curves with the Key2 model described here, where sigma is the variance here and is considered as constant because of the differential images series. F here is the computed signal thanks to the first or second order polynomial, and Y here is the experimental value. So the noise can be, so the variance here is the noise of the detector, and is considered as the sum of the CDS noise we have measured earlier, and plus the signal into the conversion gain here. So we fit our ramp with these two functions, and then we want to compare them to select the most accurate model. So to do that, we use the AKIK information criterion, and this criterion, well, in the case of using Key2 to fit our curves, said that the delta chi-square between the chi-square of the two models have to be inferior to -2 to choose the second order model. So if we say that the delta chi-square is the chi-square of the second order minus the chi-square of the first order, well, the selection criterion is that it has to be inferior to -2 to choose the second order model. And so in this fit, the flux is estimated as the 0th order coefficient of the model chosen. So here you have the results. So we can see that for the first and the second order polynomial, the estimated flux in median around the detector is not so different. But we can see that the delta chi-square is superior to -2, still in median around the detector. So here we have to notice that the chi-square here is reduced, so is normalized by the number of points considered into the ramp, because it's not the same number of points for each pixels of the detector, because the saturation level doesn't occur at the same point. But here, for the delta chi-square, is the chi-square not reduced, the initial one. Well, so that's a median around the detector. So if we rely on this value, we will choose the first order polynomial to fit our ramp, but we can wonder what happens for the pixels with the delta chi-square inferior to -2. And here we have only 9% of pixels with this criterion. And the flux estimated on these pixels by the two model is similar at 3%. So we decided to use the first order polynomial to fit our ramp. So here you have an example of a series of differential images with the in blue, the fit. And here's the equation where A0 is the 0th order coefficient and is what we will consider as a flux, and A1 is the loss of signal because of the non-linearities of the detector. And here you have the residual with this fit. So the conclusion of this study is that we will compute the flux as the 0th order coefficient of the first order polynomial fit. But as you can see, well, with this figure here, we have some decrease of the series of differential images. So that means that the detector is not truly linear, as we have said. And so we also can compute the deviation from linearity. So to do that, we compute the difference between the ramp and the linear approximation at a level of 80% of the ramp before saturation. And then this quantity is normalized by the linear value. So here you have a map of the deviation from linearity for in this detector, and here's the associated histogram. So when we do the computation, it's equivalent to compute the deviation from linearity as this formula. So the loss of signal onto the flux multiplied by the coefficient here, which is the coefficient at 80% before saturation divided by 2. And so we will consider good pixels if this deviation is within 3 sigma. And for this detector, we have 99.7% of good pixels. So it shows that this detector is has a good linearity. And finally, I will quickly speak about the dark current. So to measure the dark current, we work on a file taken into the dark. So here you have an example of the ramp, and we will fit the flux and compute the flux as with the method explained just before. And so here in the file, you can see that here at the start, we have a strange phenomenon. So it's linked to the persistence. So it's it's charges which are which remain trapped by the detector because of previous illumination. So we are not working on the first part of the ramp, but we will compute the dark current only on the 19 last frame of the 100 last frame of the detector here. And here we find a median current of 0.02 electrons per second. So it's a very low dark current. So to conclude here, the force detector has a low readout noise with 30 electrons after correction by the reference pixels. We can estimate the flux at the 0th order coefficient of the fit on 80% of the series of differential images. The detector has a good linearity, and the dark current is quite low also for this type of detector. So we have still analysis to do on the data provided by CA to characterize this detector. And we also are working at IRAP with the engineering chain, to characterize not only the detector, but all the parts of the detection chain. So that's all from, if you have any questions.
Thank you, Alix. Any questions for Alix? Yes, Alan.
So I didn't. There's a part I didn't quite understand. So your nonlinearity correction. You have two models, and you're choosing between them on the basis of the chi-squared of the fit. Do you do that for each frame, or do you do that once for each pixel, and then you have a model for each pixel, and that's the same for every frame, or do you do that every time you take a frame?
The model, well, we can do that for each frame because it's a model using all the frames of the detector, but we do that per pixel. Well, each pixel has got its own fit because they don't have the same behavior. So each pixel is fitted independently of the others.
Yes, but you do that every time you take a frame, or you do it once, and that's your nonlinearity model for that pixel that you always use?
We use the full ramp, Alan. I don't know if this is a question.
So no, my question is,
at the end of the ramp, we do that.
If I have two exposures, okay, do you determine for each pixel in each exposure independently the model you're going to use, or do you have one model that you apply to both of them?
Well, in the end, it's the same model for all pixels because the model seems to be accurate for all the pixels.
No, I know it's different for all pixels, but I'm talking about the same pixel in two different exposures.
Mm-hmm.
Well, I think the model will be the same, but for the moment, I only have data to test that on one type of exposure, one exposure. So with another flux, I will reduce this work to be sure that the model chosen is available, well, is accurate for all the fluxes.
All right, thank you.
Okay, thank you. Any other questions for Alex?
Maybe Jean-Luc can give some words about the sensor, on the performances of the two scientific sensors. Just few minutes, 1 or 2 minutes.
Yes, of course. Jean-Luc?
It would be interesting.
Yes. So we have there were 4 sensors built by the Lindred company. They are now under test at CEA, and 2 of them have are, say, science grade. As shown by Alex, one is significantly better than the other, but both of them will go through testing with entire testing, which includes the characteristics that have been shown by Alex, but also QE that will be measured in the next weeks, and intrapixel response. And this will end at the end of January. And at that time, we will choose the sensor that will be dedicated to CAGIRE. This is the situation now.
Okay, so that was going to be my question. When will we know? And you're saying January, more or less.
Yeah.
Okay.
We have started discussions very recently, discussion with ESA of the best way to proceed. It is not clear now if the sensor will be lended to CAGIRE or given to CAGIRE. Mm-hmm. It is not, there is not really difference. The only difference is that it may change the paperwork for exportation to Mexico if the sensor belongs to Europe or if it belongs to ESA.
Okay.
So, but we have just started these discussions.
All right. Thank you. Stéphane, is there anything you would like to add?
No, nothing.
Okay.
Nothing more. Thanks.
All right. Well, if there are no other questions, then thank you, Alex, again for your talk. And Rosa Becerra tells me that we have a slight change in the schedule, which makes her the next speaker.
Yes, sorry.
Yeah. So Rosa, please.
Christoph had an emergency and...
Yes, I just have to send us. Christoph is really sorry, he got a small delay, so he proposed to give the talk on Mistral tomorrow.
Yes, so Rosa will now speak on DOTI observations of gravitational wave sources during O3. Rosa, please.
Okay, good morning and good afternoon if you are in France. My name